Question A3. This question is about internal energy and thermal energy or heat. So distinguish between internal energy and thermal energy. So internal energy is the energy that is made up from the kinetic energy, your KE, your kinetic energy, plus your potential energy, your energy that is from the bonding process. This gives you your internal energy. This is your internal energy. Hopefully you will write this in a decent sentence. Where thermal energy is always dealing with a transfer of energy. It's the heat transfer. So thermal energy is the energy transferred from one body to another body when there is a temperature difference. So that is your thermal energy. Thermal energy. B. Describe with reference to the energy of the molecules the difference in internal energy of a piece of iron and the internal energy of an ideal gas. So for a piece of iron, your internal energy, I'm going to call it U, your internal energy is made up both of your kinetic energy and your potential energy. So you've got both your potential energy and your kinetic energy making up your internal energy. This is for your iron. Where for an ideal gas, we define an ideal gas with the idea that there is no bonding energies. There's no force of attraction between the particles, and so for an ideal gas, your potential energy is equal to 0 joules. So all the internal energy U for an ideal gas is made up of your kinetic energy, your movement of the particles. Now we have a question dealing with heat transfer. A piece of iron is placed in a kiln. A kiln is something that is used to heat up objects. It's like an oven, until it reaches a temperature of theta in the kiln. The iron is then quickly transferred to water held in a thermally insulated container. The water is stirred until it reaches a steady temperature. The following data are available. So we get given the thermal capacity of the piece of iron, the thermal capacity of the water, the initial temperature of the water, and the final temperature. Now, you've just got to be careful with this thermal capacity, because here they're not giving us a mass, but it just means that for this piece of iron to increase by 1 Kelvin, you need 60 joules of energy. And for this mass of water, for this volume of water, to increase it by 1 Kelvin, you need 2000 joules of energy is required. So where you have usually your formula Q is equal to MC change in T, now you would have the formula Q is equal to, we call this big C, this is your thermal capacity change in T. Important to realize that. So state an expression in terms of theta and the above data for the energy transfer of the iron in cooling from the temperature of the kiln to the final temperature of the water. So we want to see here for the energy transfer that actually took place. Well, for the iron, what happened was that the energy transfer for this is going to be your big C, which is 60. And now we look at a temperature change. Now the final temperature of it is this, and its initial temperature is theta, so it would be theta minus 45 would give the change in temperature. That would be your change in temperature, and that would give you your energy transfer, the amount of energy transferred. And then calculate the increase in the internal energy of the water as the iron cools in the water. So for the water, you're going to have a Q is equal to also big C delta T. But here our heat capacity, our thermal capacity is 2000 times by our change in temperature. It went from 16 to 45. So there it went up 29 degrees. Is that correct? 29 degrees times 29. And when you put that into your calculator, you should get something like 5.8 times 10 to the 4 joules. Okay? And then use your answer in C1 and C2 to determine theta. So what we're saying here is that this here is the Q lost, and this is the Q gained, and they must be equal because we have stated that the thermal capacity of the container and the insulation is negligible, and also because it's a thermally insulated container. So we're assuming that all the energy lost from the iron goes into the water. And so I can therefore put this 5.8 times 10 to the 4. I can say that must be equal to the 60 times theta minus 45, and solve that equation, which is pretty simple to do. And once you've done that, you should get your theta is equal to 1000 degrees. It's actually it's degrees Celsius. When that's after you've rounded it down.